So this is a bit of a warning to you all that are here, and an apology to people that try and watch on YouTube, because today's lesson sucks on YouTube. Today's lesson is going to be very, very visual. You are going to be using what's called, I'm going to be teaching you what are called the right hand rules, and these are tricks that you can use using your right hand and holding it in certain ways to predict directions of magnetic fields and of forces. So you want to be prepared to participate here. Read along with me. It says this: magnets are dipolar. They have two poles. What are the poles of a magnet called? North and south. So if this is a standard magnet, just arbitrarily, I'll put the north pole on the left side and the south pole on the right. Here's our standard bar magnet. And just like in electricity, like poles repel and unlike poles attract, in the same way that like charges repelled and unlike charges attract. However, unlike electricity, Sarah, it's impossible to completely isolate a north pole from a south pole. We are able to isolate a positive charge. It's a proton. We are able to isolate a negative charge. It's an electron. What would happen if I cut that magnet or broke that magnet right there? Would I have one magnet that was all north and one magnet that was all south? Nope. I would have a south pole right there and a north pole right there. I haven't checked the research lately, but 5 or 6 years ago I would have said, if you can figure out how to isolate a north pole or how to isolate a south pole, probably a Nobel Prize in physics for you, because that would be handy. But as far as I know, it can't be done. Yet. Magnets send out magnetic field lines in the same way that electric charges send out electric field lines. And just like with electric field lines, we have to define the direction. With electric field lines, we said, which way would a positive want to move if it could? They went from positive to negative. The direction for magnetic field lines, from north to south. They point away from north and towards south. Or, in terms of a compass, the direction a compass needle points. A compass points south. Wait a minute, Mr. Duick. I've seen compasses. I thought they point north. No, a compass points south. Wait, Mr. Duick, I don't mean to argue with you, but I was in Boy Scouts, I was in Brownies, I've done some camping. A compass points north. No, a compass points south. This is true. A compass needle points south, not north. You may think it points north, but I'll explain to you how that works in a second. We need a symbol for magnetic field. Can we use M? Why? Yeah, for what? For mass. And capital M also is used for something else. So, sorry. Capital B. In fact, you're often going to hear me refer to a magnetic field as a B field. I think it's from a Latin word. Okay. It is a vector. Oh, yeah, because it points from north to south. What are the units for magnetic field? Does anybody know? There are sort of two. One is Gauss. We're not going to be using that, but you can measure magnetic fields in Gauss, named after a mathematician whose last name was Gauss. But the standard SI unit is the Tesla, capital T. Yes, he has a unit named after him. And of course it should have something to do with electricity and magnetism. Got something to write with now, Kieran? Next time, bring something to write with. Earth's magnetic field is around, because anytime I introduce something new to you, I like to give you an idea of what's really big and really small. Earth's magnetic field is around 10 to the negative 6 Teslas, 10 to the negative 7 Teslas. That's enough to move a compass needle. Very large field. That's a huge field. 4 Teslas.
Bless you.
In fact, something around the order of 30 or 40 Teslas, I suspect long-term exposure to humans would eventually be fatal because it would probably alter the iron in the hemoglobin in your blood, and that would be a bad thing. Okay? So a Tesla, much like a Coulomb, is large. Put your pencils down, look up. There are 2 main types of magnets. There are what are called permanent magnets made out of ferromagnetic materials. Those are the ones that go on your refrigerator. Those are the rare earth magnets that I was playing with a little bit earlier. But then there are electromagnets. This is a magnetic field caused by a current. This gives us a magnet that we can turn on and off. And that is really, 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 really useful. Hugely useful. What do the magnetic field lines look like around a single magnet? As you can see, all the magnetic field lines point from what to what? North to south. That will be a question I will ask in the future. You'll need to know that. This is also the direction a compass would point. If you put a compass, for example, right there, it would point that way. If you put a compass right there, it would point that way. If you put a compass right there, it would point that way. Also, unlike electric field lines, which start on a positive and end on a negative, magnetic field lines have no beginning and no ending. If you ask me what's going on inside the magnet, I guess don't write that down. It would sort of be doing that, but we're not going to really talk about what's going on inside the magnet. That's more difficult. The Earth is also a magnet. That's how a compass works. At the North Pole, what does the magnet inside the Earth look like? So I've told you that magnetic field lines point from what to what? Which means, since that's the same direction that a compass points, it means inside the Earth's magnet looks like that. Now, geographically, we call this, but it's the south magnetic. Now, here's the problem. They'll refer to the north magnetic pole up there at the North Pole. It's not. It is a south magnetic pole. Magnetically. Geographically, it's north. It's the opposite of what you think. The North Pole has underneath it a giant south pole of a magnet. It has to, because that's which way a compass points, and compasses point in the direction of the magnetic field, and magnetic field lines point from what to what? North to what? To what? To south. Okay? Because when they were defining directions, and we've known about compasses for about 1,000 years, but we didn't know why they worked. Like the Chinese had compasses way back when. We knew we had this thing that we could make that would always point in the same direction. Let's call that direction north. Okay. What would the magnetic field lines look like between 2 bar magnets where identical poles are facing each other? Pause for a second. What does magnetic field lines look like? Well, if a north pole, we have like poles here. Like poles do what? Repel. So it's going to look something like this. A magnetic field line would start this way and it would go kind of like that. Another one would go kind of like that. We might have one start here and go kind of like that. Kind of like that. Oh, I did that one wrong. I went from south to north. Good gosh, I'm out of practice. From north to south. We would have a line kind of get repelled that way. It would vanish off the screen, and it might come back in this way. We would have, for example, a line kind of go like that. Another line like that. And if you just kept drawing stuff along these, no pun intended, lines, you'll get pictures of magnetic field lines. Yeah, Tristan, it's pretty cool. Okay. So you give it a shake. If you pull the magnet out, you'll see the magnetic field lines all vanish again. Okay. And then put it back in, give it a shake. Magnets are cool. This next part is really important. Symbols. We're going to find, Lena, that we have to draw three-dimensional pictures. But we're going to be drawing three-dimensional pictures on two-dimensional pieces of paper. And so we've come up with some shorthand to show direction. If I want to show something is going into my page or out of my page, because to draw that is very, very tricky, we're going to use an X with a circle through it, and that's meant to be the tail feathers of an arrow going away from us. We would see the arrow's tail feathers. That's to show that something is going into the page. We're going to use a little dot with a circle, and that's meant to be the point of an arrow coming out of the page towards us. That will be our abbreviation to show out of the page. And you're going to figure out how that works in just a few minutes. Okay? Pause again, lots of pause. So, a wire that carries a current, it turns out, this is the key to this unit, generates a magnetic field. A compass wire will be deflected if that wire, a compass near a wire, say compass wire, a compass near a wire will be deflected if that wire is carrying a current. Video of that I don't. Here is the question we want to ask. If a wire is carrying current, it will generate a magnetic field. What direction is the magnetic field? Braden, put it down for a little bit. You can play with it in a second, but temporarily just stand it up on its end and put it down out of your viewpoint. We'll come back. Okay, this is important. This is right-hand rule number 1. Put a star next to this. If you want to figure out the direction that a wire is creating for a magnetic field if it's carrying a current, you imagine holding the wire in your hand. This meter stick is the wire. You point your right thumb in the direction of the current. Your fingers curl in the direction of the magnetic field. So right now, in front of this wire, closest to you, which way are my fingers pointing? Down. The magnetic field right there is pointing down. What about right here, beneath the wire? Which way are my fingers pointing? The magnetic field beneath this wire is going to be behind me, away from you. Right now, on this side of the wire, which way are my fingers pointing? The magnetic field here would be pointing straight up, and if I'm flexible enough, the magnetic field above the water will be coming out of the page towards you. The magnetic field above the wire will be coming out of the page towards you. This is the right-hand rule. You imagine you're holding, this is right-hand rule number 1, there's 3 of them. You imagine you're holding the wire, you point your thumb in the direction of the current, your fingers curl in the direction of the magnetic field. Now, there is a way to get these wrong, and the way to get these wrong is to try and have your hand all tucked in and embarrassed. Get your hands way out when you're doing these. It makes it easier. Okay? That's right-hand rule number 1. So, app. That's what I had. I had an app. Here's a wire looking right down the wire. Which way is the current moving? What does that X tell me? What did I say at the top of the page? So all of you right now, Caleb, put that away for just a second, and I'll give you time to play with it later. All of you right now, point your right thumbs straight into the page. Which way are your fingers curling? Which way is the direction of the magnetic field? Right. Well, you can't use right or left because it goes in a circle. Clockwise or counterclockwise? So for me, I point my thumb into my screen, and I get that the magnetic field is in this direction, yes? So we'll label that as B. So, don't write this down. Which way would a compass point right where I've circled? Now you can use left. Good. Which way would a compass point right there? Up, top of the page. Which way would a compass point right there? To the right. Which way would a compass point right there? Down the page. Supposing I gave you a picture of a wire and I told you the magnetic field. What do those little dots above the wire mean? Which way is the magnetic field coming? Which way is the magnetic field going underneath the wire? So hold your right hand in such a way so that if you were holding this wire, it would be coming out of the page above it and into the page below it. You have to hold your right hand. Get the pencil out of your hand. Okay? So you're either going to hold your hand this way or this way, right? Because that's which way the current is going. With me so far? So I'm going to use my board right now. If I hold it this way, if I point my thumb to the left, above the wire, I'm going into the page, and beneath the wire, I'm coming out of the page. That's not correct, is it?
No.
I have to be holding my thumb this way. That, Sarah, allows my fingers to come pointing towards me above the wire. I'll even hold the wire there to make it easier. So above the wire and below the wire. So which way is the current pointing? To the left or to the right?
Clockwise.
Your right hand has a built-in magnetic field determinator. Sometimes the question will, instead of saying current, which is which way positives flow, they'll talk about electrons. You can either use your left hand. I don't prefer that method. Instead, I just point my thumb in the opposite direction. An electron moving up is the same as a proton moving down. An electron moving south is the same as a proton moving. I'll do that. So here is a picture that I found online of right-hand rule number 1. I said we could make electromagnets, electric magnets, magnets that are turned on and off by electricity. One wire is a start, but then we have something called a solenoid, a very useful electric device. If we take the same wire and we coil it around and around and around and around and around in many loops, all in the same direction, never changing direction, all in the same direction, we call this a solenoid. What would the direction of the magnetic field generated by a solenoid be? Because if one wire makes a magnetic field, what if you wrap a whole bunch of them side by side by side by side by side? Here's a picture of a typical solenoid. We also have learned that we can dramatically increase the strength of the magnetic field by, instead of just wrapping the wires around a piece of wood, wrap it around an iron core. That will dramatically increase the strength of the magnetic field. We call that an electromagnet. Lena's going to put her phone away. She's not that important. Okay, sorry. An electromagnet has thousands of uses. Turn the page. So here is right-hand rule number 2. This is the right-hand solenoid rule. How does this one work? Again, my apologies to those of you at YouTube who are trying to figure out what the heck I'm talking about. Caleb, have you passed it on yet?
No.
You can pass it on now. Or you can play with it first and then pass it on for a second. Okay? Yeah.
I like the Adventures movie.
No, pass it to Matt now, though. And then Matt, hang on again, and I'll have your attention back here. So the right-hand solenoid rule is this. You imagine holding the solenoid, this coil of wires, in your right hand. You curl your fingers in the direction that the current is going through the wires. Your thumb points north. We're going to practice this a whole bunch, but this is the right-hand solenoid rule. By the way, if you're trying to do this, this is one of the few times... Who are my lefties here? We have an advantage because we can hold the pen and do the right-hand rule. Those of you with right hands, if you try doing this while holding a writing utensil, it's going to botch you. You're going to be holding your hand differently. That's why I barked at you. Get the pen or pencil out of your hand. So you ready? It says, what direction is the magnetic field below? I haven't given you a solenoid yet. Didn't say put your pencil down yet. I'll show you how we draw a solenoid. Okay, here's how we draw one. What you do first of all is you need a battery. And then you run it like this. Oh, hang on, Mr. Duick, it's going to go behind. And then to make it look three-dimensional, to make a solenoid look like it's three-dimensional, we use long looping S's or reverse S's like this. Can you see how that gives it kind of a 3D look? And then I'll have it duck behind and come out. There is my sketch of a solenoid. It's one of the few figures that I can draw. So draw something identical to me, which means your S's will be reverse S's, right? And once you've drawn that, let's label the current. Follow it, follow it, follow it, follow it, follow it. I guess the current goes this way, ducks under, goes this way, goes this way, goes this way, goes this way, goes this way. Now, if you're right-handed, lose the pen or pencil once you've drawn that. If you're left-handed, one of the few advantages we have, imagine you're holding that solenoid in your hand. Now, I guess you're either going to hold your hand this way or this way. Hold it so that your fingers curl in the direction of the current. Now, I'm going to face my board so I'm in the same direction as you. Can you see, if I hold it this way, this is incorrect because my fingers are coming over the top and downwards. Look at the current. Isn't the current coming over the front upwards? So I could not hold it this way. I have to hold it this way. Can you all hold your right hands like that, please? Okay. Which way is north? So this tells you that that will be the North Pole and that will be the South Pole. We're going to go back one question because I didn't analyze this solenoid right here. I don't know if your diagram is clear enough that you can, but I'm going to zoom way in on mine. If I look at mine, because this is a color diagram, yeah. No, the north will be whichever way your thumb is pointing. That's the rule that I gave you. Okay? I can come up with all sorts of different ways to wire these and draw these. Okay? Here, Caleb, leave me alone, please. There's the current, yes? There's the current. It looks like in my diagram, when I zoomed in, I'll zoom even a bit more. Oh, can't go that big? Oh, got an extra zero there. I think my diagram ducks behind, and then on the solenoid itself, I think I'm going that way. Am I not? Hold that solenoid in your hand so that your fingers curl in the same direction, your right hand, in the same direction as the current. And the only way that I can hold, if I hold it this way, my fingers are curling in the wrong direction. I have to hold it this way with my thumb pointing what direction? This is the North Pole. This is the South Pole. When there used to be a provincial exam, the first year I was teaching physics, the kids were writing in the library, and as the physics teacher, I wasn't allowed to be in the room. Another teacher was supervising. And about an hour into the exam, my phone rang. Mr. Duick, this teacher said, "You're going to be so disappointed in your students. I know how much you care about them and how hard you've worked to teach them. They're cheating, Mr. Duick. They've come up with these bizarre hand signals, and they are signaling each other all of the answers to the questions, Mr. Duick." And I had to explain to that. No, they're using the right hand rule. So from then on, every year, I would tell whoever was supervising the exam, hey, about an hour in, you're going to see kids making all these weird hand gestures. It's not a code. Oh, and they're going to be holding their hands way out because that's how I've taught them. They're going to be holding their hands way out. They're not trying to cheat. I still remember that first teacher felt so bad. They were like, oh, Mr. Duick, you're going to be so sad. No, they called me first, thankfully, and I explained it. This idea of having a magnet that you can turn on and off, or if I hook it up to alternating current, that I can have north, south, north, south, north, south. This is used in a whole bunch of our electric devices. We use them in transformers, not the toys, the electric device. Motors, generators, television, speakers, doorbells, fire alarm bells, cell phones, power door locks. So power door lock, for example, especially the older style, when you first pushed the power lock, I'm willing to bet all you did is you activated a magnetic field solenoid north that would pull that lock down on the old style where the locks actually went into the door. Now locks go forward and back, but it's the same idea. Our fire alarm bells, I guarantee all that's inside there is, well, I can show you a picture. My friend lives in a very old building. Example 5. This conductor on the left carries current into the page. That's what those tail feathers mean. This is carrying current out of the page. That's what that dot means. Draw the lines of force around each conductor showing their direction. I'll do the left one first. So all of us, we would point our thumb into the page. And I think on the left-hand wire, right at the top, which way am I going to point this arrow? To the left or to the right? Goes clockwise. What about on this wire? I'll point my right thumb out of the page, and I have a magnetic field that goes that way. Would these conductors attract or repel each other? What direction is the magnetic field from each one right there? Like or unlike? Aren't they both pointing straight down? Those are like magnetic fields. What do like magnetic fields do? This is actually something we have to take into account. This is why when you're wiring, you want to spike or nail down the wires on regular intervals, usually every 15 centimeters or so, because they will actually, if it's direct current, they can repel or attract each other. And if that happens over and over and over, they can start to wear loose, and loose wires are bad things. So which end of this solenoid will be north? Try this on your own. I'll do it up here with the screen frozen. Get that? Now, which way do magnetic field lines point? From what to what? Say it again, from what to what? So let's draw a magnetic field line right now from north. So, and let's put arrows like that. So right where the word figure 7.10 is, which way would a compass point? Left. A magnetic field has no beginning and no ending. If I continue this inside the solenoid, which way does the magnetic field point? It points to the right. So the rule that I've given you tells you which side is north and which side is south, and the lines rule that I've given you work outside the solenoid. You might be saying, Mr. Dewick, inside the solenoid, now it's pointing from south to north. No, it's just continuing the loop, thank you very much, because magnetic field lines have no beginning and no ending. Okay. The third one is the most difficult, but the most useful. This is right-hand rule number 3. It's called the right-hand motor rule, or Ampere's rule. When Sarah's done yawning, we'll continue. The reason this is called the right-hand motor rule, Sarah, is this is what explains how electric motors work. This is also what explains how electric generators work, and we'll dive into that in a few days. Suppose we have a wire carrying current through a magnetic field. So here's my wire. There's the battery. Which way is the current coming from this battery? Pointing left or pointing right? Let's all draw a little arrow pointing right along the wire. And then those dots, Kieran, those dots are an external magnetic field. So here's a wire, and we're putting it through a magnetic field. Which way is that magnetic field pointing? Those dots are pointing which way? What does that tell me? Out of the page? We'll usually call that as out of the page. Okay. This magnetic field will exert a force on the wire itself. This wire, because it's creating its own magnetic field, will interact with the magnetic field that's coming out of the page, and it will feel a force. To find the direction, step 1. This one is the most complicated one, so put your pencils, if you're right-handed, out of your hand. You're going to point your thumb in the direction of the current. Your right thumb. You're going to point your right thumb. Tristan, your right thumb. Hands out. Tristan, oh, sorry, I'm pointing. Wow, I'm looking at my diagram. I apologize. Let me reverse it. That way. Okay? Except don't hold your hand like this. Hold your hand like you're going to give the biggest high five you've ever given. Okay? The key to this rule is no, please don't do that. Okay? Sorry, Manir was showing, don't do that. The key to this is don't bend your fingers like this, and don't bend your fingers way back. You want a nice flat hand, like you're giving that's why I said a high five. Okay? Thumb in the direction of the current. You're going to point your fingers in the direction of the magnetic field, which means all of us are going to have to bend, like that. Yes? Don't bend your hand, Kevin. Bend your arm. Your hand stays in high five mode. Bend your elbow. Kevin, ready? You got to go like this. You were doing this. I said, don't bend your hand. Bend, okay? Hand stays in high five mode. Yes? Okay? Kyle, do it. Okay? This is magnetic yoga here. Your palm points in the direction of the force. Which way is my palm pointing? This wire is going to get pushed down the page. Okay? So read the 3 steps here. I said this. You point the thumb of your right hand in the direction of the current. Point your fingers in the direction of the magnetic field. Your palm pushes, and this is how I remember palm push, in the direction of the net force on the wire. So but what you have to resist is what Kevin was inadvertently doing. The reason I barked at Kevin is he did this. That was great. And he said, oh, I'll point my fingers in the direction. Which way is my palm pointing now? Behind me. Hand flat. Bend. Now it's obvious. Palm down the page. Usually they won't be quite as acrobatic as this first one that I gave you, but I did that on purpose. Here's the wire. Which way is the wire carrying current? It's not away. We call it into the page. Okay? What direction is the magnetic field pointing? To the left? Which way will this wire feel the force? So, you're all doing it wrong already. Your thumb points in the direction of the current. All of you right now should be pointing your thumbs straight into your paper. All of you should be pointing your thumbs straight into your paper. What direction is the magnetic field? First of all, stop doing this. For the right-hand motor rule, got to have our hand flat. Okay, so you ready? So that we're all doing this the same. Everybody with your left hand, hold your paper up so it's vertical, so that it matches my board. So this is what you're doing. You would point your thumb in, and by the way, if you find you can't bend a certain way, tilt the paper at a different angle, and then you'll be able to bend the correct direction, Kevin, okay? So, all of you right now, you're holding your paper like this, Kevin, yes?
Yeah.
Thumb goes like that, yes? Which way is the magnetic field? Pointing to the? Yeah. Oh, wait a minute. Yeah. Okay? Which way is my palm pushing? It's easy to push up the page. Okay? For me, on my computer screen, my thumb points into the page. My computer screen has the magnetic field going that way. Which way is my palm pointing, Lena? Up the page. We're going to practice a bunch of these. Just to convince you that I'm not making this up, Lena, we're going to practice a bunch more of these. An electron traveling to the right enters a magnetic field as shown. We don't do electrons. We do current, which is positive. An electron traveling to the right is the same as a proton traveling which way? So we're all eventually going to point our thumbs to the left. What direction is the magnetic field? What do those X's mean? Into the page. So if you want to match me, if you hold your paper vertical, you can. If that's my board, I would point my thumb to the left, because the electron to the right is the thumb to the left. Fingers into the page. Which way will this electron field force? Yep. Don't do this with your TVs. A proton enters a magnetic field along the line shown in the above diagram. What direction is the magnetic force? So again, if you want to match me, you can hold your paper up vertically. If you're feeling comfortable and you want to try this on your own frame of reference, that's fine. For me on my screen, I would say this proton is traveling this way. Which way do magnetic field lines point? From what to what? Everybody right now with your pen, draw magnetic field lines pointing that way from north to south. There's my magnetic field lines. And so Sarah, thumb goes like this. Sarah, which way are the magnetic field lines pointing? To the, looking for what means letter R?
Right.
Okay, this, oh, I was going to bend like this, and I said, wait a minute, why don't I just do that? Ha, that worked better. I was going to try bending all the way over, and then I realized, stick my hand out this way. Which way is my palm pointing? Which way is this proton going to get deflected? And now you're starting to see how we can actually deflect subatomic particles. A, B, C, or D? D? Oh, I got lots more? Good. We need to practice this. The above diagram shows an electron traveling to the right. Nice try. An electron traveling to the right is the same as a proton traveling which way? And it hits a magnetic field. Which way are these magnetic field lines? From north to south, so I'll draw those in. What direction will it be deflected? Try this one on your own. When you're done, circle your best guess, A, B, C, or D, without blurting out an answer. Okay? And again, Kevin, I'm going to criticize. You're doing this. Get your arm out, trust me, because that also lets you figure out that you can, I can flip it this way and not have to bend so much. I've done this before. Are you done with my toy?
Oh, yeah.
It's A or B, yes? I didn't say which one it is, but definitely A or B. Is it A? Let's find out.
Maybe.
Nope, that's no good, Mr. Dewick. So, electron traveling right, that's the same as a proton traveling that way. Magnetic field is that way. Yes? I'm getting my palm pointing out of the page. B. Number 11. Which diagram best illustrates the magnetic field lines around a wire carrying conventional current? This is not the rule that we were just doing. This is also not the solenoid rule. This is the very first rule. So what direction is the current in the wire in all four pictures? What does that dot mean?
Out of the page.
So all of you right now should be having your thumb, Braden, pointing out of the page. Your right thumb. What direction? What's the correct direction of the magnetic field? A, B, C, or D?
Counterclockwise.
A, B, C, or D? A, yes? Oh, this is going to be the solenoid rule. You know how I can tell, Lyndon? Because they gave me a picture of a... Hey, that works. I'm going to zoom in a little bit. Now, if I'm looking at the current, before I start pointing, I got to draw the current out. So Current goes from positive, it goes this way. It looks like it ducks behind, and then I think it's coming up from the bottom, pointing up. Yes? So I'm going to hold the solenoid in my right hand without a pen or pencil in my hand. I'm going to curl my fingers in the direction of the current. What's north, X or Y? X, I agree. So this part has two questions. First of all, polarity, I'm going to say yes, no, yes, no. Now, the magnetic field outside goes like this, goes like that. Which way does the magnetic field point inside the solenoid? Yeah, from Y to X inside the solenoid. No, no, yes, yes. What's the correct answer? A, B, C, or D?
Give it to C.
And if you haven't started answering these chart questions that way, it's high time you did. Okay, now I see a current carrying wire and an external magnetic field. That's going to be the right-hand motor rule, the one that the twisty one. So let's follow the current this way. I guess down here the current is going that way. Which way is the magnetic field? Magnetic field lines always point from what to what? So the magnetic field is going this way. Try this one on your own. It's going to be A, B, C, or D. Don't blurt out your answer.
I'm not helping you.
Brandon, what'd you get? You were right. A, B, C, or D? B. Down. Okay. This is one of the methods that we can use when we're studying unknown subatomic particles to figure out whether they're positive or negative. So example 14 says this: a beam of positively and negatively charged particles enters a magnetic field as shown. Which path illustrates the positive charges and which path illustrates the negative charges? Well, let's assume they're all positive. So all of us, let's point our thumb in the direction of the current, which I think is going to be pointing to the right. Which way is that magnetic field with X's in it? Which way will a positive charge get deflected? So for me, I go boom, boom. I'm getting this, yes? Yeah?
Yeah.
Okay. By the way, if you're just sitting not trying this, you're in trouble. You've got to do this and try this with us. Make your mistakes and fix them. Which way will positives get deflected, Mitra? And my palm is pointing up. So what direction is positive? I. What direction is negative? The opposite of positive, which would be? Okay, so yes, yes, no, 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 yes, no, yes. What's the correct answer? A, B, C, or D? And I apologize, but next weekend you all have your dry grad. I can't give you your May long weekend without homework. I couldn't think of a way to do both. So I'm going to try and make it so that next weekend you don't have much homework, but you're going to have homework for the May long weekend. You got 4 days. Do some homework. Last one. An electron enters a uniform magnetic field as shown below. Oh, which way is this electron traveling?
To the right. So
Which way is the proton traveling then? So all of us, we're going to point our thumbs to the left. Which way is the magnetic field pointing? So put your hands in high-five mode. Which way is the magnetic field pointing?
down.
No, which way are the arrows pointing?
Left.
Why is this? What's weird about this one? Okay? So what we're going to learn, and this is, I do this on purpose, Lena. In the next lesson, we're going to learn a charge is only deflected if it's cutting across magnetic field lines. If it's going parallel to the lines like this, there's no deflection at all. It's going to keep going in a straight line.
Oh wow.
and you notice you couldn't make your right hand work that way, if you're ending up with a situation like that, first of all, check to make sure you're doing it right, but it may just be there's no deflection. What's your homework? Every one of these, because you need to practice this.